So have you ever heard of the rare earth paradox? It's a proper puzzle, actually, and it's been bothering me a little.
It's a very valid puzzle. It confuses many people, not just students.
Because, you see, we have these elements, like cerium, and they're called rare earth elements.
Yes.
The name itself says rare. So you would naturally assume they're hard to find, maybe like gold or something.
That's the logical assumption, yes.
But here's the catch, and this really surprised me. Cerium is actually more abundant in the Earth's crust than copper.
That is absolutely correct. It's surprisingly common.
Copper. I mean, the stuff we use for wires and pipes.
Yeah.
It's literally everywhere. So if cerium's more common than that, why on earth do we call them rare? And why are we always hearing about a rare earth crisis for things like electric vehicles? It just doesn't add up.
It is a very good question, and it's the perfect place for us to start. See, the rarity, it's not about how much of it is actually in the ground. The total amount is huge. The problem is, let's just say they are chemically antisocial.
Antisocial? How so?
In a way. They are very dispersed. You don't find them in a big concentrated lump like you find iron ore. And more importantly, they are so similar to each other chemically.
Yeah.
Like identical twins, maybe even triplets. Separating them is an absolute nightmare.
Ah, I see. So you dig up a scoop of earth and you have cerium, neodymium, lanthanum all mixed in, and they just refuse to separate.
Exactly. The process is difficult, it's expensive, and it creates a lot of chemical waste. But, and this is the key point for today, we tolerate this whole headache. We spend the money.
Yeah.
Why?
Why?
Because modern technology simply cannot survive without them.
And that just sets the stage perfectly for today's deep dive. We are opening up the toolkit of the periodic table. We are exploring the applications of D and F block elements.
Yes.
And this covers the final, and I think most interesting part of Unit 4, the D and F block elements.
I completely agree. And the mission for this deep dive is, very simple. We need to shift our perspective a bit.
Shift it how?
Students often look at the D and F block as just, well, a list of electron configurations to memorize, random letters on a chart.
Right. Why do I need to know this?
Exactly. But we need to see them as the material scientist's toolkit.
The toolkit. I like that.
Yes. Almost every major technological advancement, from the catalytic converter in your car to the screen on the smartphone you're probably holding right now, it relies specifically on the chemistry of these blocks. Without them, we are back in the 1800s.
That's a huge claim. So, okay, let's unpack this. At the absolute simplest level,
Zero.
Vela, how should we think about these elements?
Okay, think of it this way. You have your main group elements: carbon, oxygen, nitrogen.
Usual suspects.
Yes. They are the foundation. They are the bricks, the cement, the mortar of the chemical world. They build the main structure.
Right.
But the D and F block elements, they are the specialist contractors.
I like that analogy. So if I'm building a house, the bricks are my main group. But when I need to wire the electricity or install a high-tech security system, I don't call the bricklayer, do I?
No. You call the specialist, the electrician.
You call the D block.
Precisely. Imagine a construction site. You have your general laborers, the main group elements, doing the bulk work, but then you have these specific demanding tasks.
Okay.
You need to create a super strong structure that won't snap. You call in iron from the D block to make alloys.
The structural engineer.
Right. You need to speed up a chemical reaction maybe 1,000,000 times without getting consumed. You call in platinum, another D block specialist.
The efficiency expert.
And what if you need something to glow a very specific bright red for a high-definition screen? You call in the lanthanoids from the F block. They are the lighting designers.
So they are the experts of the periodic table. But what's really happening inside the atom? I mean, why do they get these jobs? Why can't carbon do it? Carbon is so versatile. No.
Carbon is fantastic for building backbones, but it lacks the special tools for these jobs. It all comes down to their electron configurations. For the transition metals in the D block, the secret is their partially filled d orbitals.
The d orbitals.
Yes. Think of these orbitals like flexible hands. Because they are only partially filled, they're available. They can form temporary bonds.
Like for catalysis.
Exactly, for catalysis. Or they can form strong metallic bonds for alloys. They are chemically flexible. They can shake hands with many different things at once.
Okay, flexible hands. That's a good image. But for the F block, the lanthanoids, you said it's the opposite story?
It's the complete opposite. They have shielded electrons.
Shielded. What does that mean in simple terms?
So imagine a very important person sitting in a soundproof glass room right in the middle of a chaotic party.
Okay.
The party is while temperature changes, other chemicals around, but that person in the glass room is totally unaffected. That is the feeble electron. It's buried deep inside the atom. The outer electrons protect it.
Ah, I see.
So the outside environment doesn't disturb it. This creates very pure, very specific optical and magnetic properties.
And the actinoids.
Well, for the actinoids, it's mostly about their instability. Their radioactivity is what drives nuclear power.
So before we get into more examples, if a student needs that one solid definition for their exam, something that really anchors the concept, what should they write?
Okay, let's catch this point clearly. For an exam answer, this is your anchor definition. Applications of D and F block elements exploit their characteristic properties, such as multiple oxidation states, complex formation, catalytic activity, and optical properties in catalysis, alloys, pigments, medicines, magnets, and nuclear technology.
That covers everything. I think a huge misunderstanding students have, and I probably had it too, is that this section, the applications, is just extra trivia to memorize.
That is a very dangerous mindset to have.
Why is that?
Because these elements are the technology enablers. The reason we study them is because of their applications. If you understand the application, you actually understand the chemistry much better. If they didn't do all these things, we wouldn't spend a whole unit on them.
Right. So let's make this more concrete. We use the specialist contractor idea, but let's go back to the toolkit analogy. I want to visualize opening this toolbox.
Yes. So the main group elements are like a hammer or a saw, general purpose.
You use them for everything.
Correct. But the D block elements, they are your precision power tools.
Okay, give me some examples. What's iron in this toolkit?
Iron Fe is your heavy-duty wrench. It's for combining things, for making alloys like steel that are structurally so strong. Pure iron is actually too soft.
Right.
But when you mix it, that D block magic, it becomes the backbone of all our infrastructure.
And what about platinum?
Platinum, PE, is like a precision microscope or maybe a laser cutter.
Yeah.
It's for catalysis. It manages the chemistry precisely and quickly without getting its own hands dirty.
And copper.
Copper, T, is your electrical connector, the best reliable conductor for the price.
And the F block, the specialty equipment.
Exactly. The lanthanoids are like a color selector tool in a software. They determine the exact color, the exact frequency of light that is emitted in phosphors.
In uranium.
Uranium is the heavy-duty power generator sitting in the corner. Very powerful, but you have to handle it carefully.
It's interesting because historically we used these tools before we even knew how they worked, isn't it?
Absolutely. Applications almost always come before the theory. Humans used steel for centuries. We made swords and bridges long before we knew what a orbital was.
We just knew it worked.
We just knew it worked. We used these elements to solve problems that carbon or nitrogen simply couldn't solve.
To really make this stick, I want to try a visualization. Everyone listening, just pause for a second. Picture this. Let's do a day in the life of a smartphone.
Okay, let's trace it.
You're holding your phone right now. It looks so sleek, just glass and metal. But inside, it's a D and F block party.
It really is.
Okay, it's morning. Your alarm goes off. That sound is coming from a tiny speaker. And a speaker needs a magnet, right? But not just any magnet.
Correct. You need a neodymium iron boron, NdFe magnet. That is F block chemistry right there. Neodymium is essential for these super strong permanent magnets. Without it, your speaker would be the size of a brick.
Okay, so I turn off the alarm, I tap the screen, and it lights up. Those pixels, they're not magic.
No, they use lanthanoid phosphors.
Phosphors, so that's where the color is coming from.
Yes, you have cerium helping with the white backlight. You have europium making those vivid reds. You have terbium for the brilliant greens.
All F block elements.
All F block. And remember those shielded electrons in the soundproof room?
Yes.
Because they're so protected, they give off very pure, precise colors. If we use D block elements, the colors might be messy or change if the phone got hot. The F block gives you that HD clarity.
That's fascinating. Okay, my phone has been charging the battery.
It most likely uses cobalt, Co, in the cathode. That's a D block transition metal. It's key for energy density.
And as I start using it, the processor gets hot.
And that heat is being conducted away by copper, K-wiring, and heat sinks, another D-block property at work.
And finally, I take a picture. The camera lens, the tiny motor that focuses it.
It often uses tungsten W alloys because it's very tough and heat resistant.
So without D and F block chemistry, my phone is, well, what is it?
It's a paperweight, a brick. You wouldn't make a sound, it wouldn't light up, it wouldn't hold a charge. It is literally built from these specialist elements.
That really puts things in perspective. Let's look at another one, maybe something we see every day. Cars.
A classic example, the catalytic converter.
Right. It's in the exhaust system. What exactly is going on inside that thing?
So inside, you have a ceramic honeycomb, and it's coated with a very thin layer of rare transition metals, platinum, PD, palladium, PD, and rhodium, Rh.
The expensive ones.
Very expensive, but absolutely essential. And here is where those flexible hands we talked about come in.
Okay.
The exhaust from the engine has toxic gases. Carbon monoxide, CO, nitric oxide, NO, very bad stuff. As these gases pass over the metals, the metals use their partially filled d orbitals to form temporary complexes. They basically grab the gas molecules for a moment.
Just for a split second.
Exactly. They hold them, weaken their bonds, help them react to form harmless gases like carbon dioxide and nitrogen, and then, this is the magic, they let go.
They let go.
Yes. The metal is not consumed. It's a true catalyst. It just facilitates the handshake. Main group elements can't do this. They'd either not grab at all, or they'd grab too tight and never let go.
And the result is cleaner air in our cities. That's a huge application. Let's switch to medicine. MRI scans. This one is really cool.
Yes, magnetic resonance imaging.
If you know someone who's had an MRI, they might have been injected with a contrast agent. And that agent is almost always based on gadolinium, GD.
Correct. Gadolinium, an F-block element.
So why gadolinium? Why not, say, iron or calcium?
Because the gadolinium ion, GD, has 7 unpaired electrons in its 4 f orbitals. 7.
That's a lot.
Which makes it highly paramagnetic.
Meaning it interacts very strongly with magnetic field.
Very strongly. In the body, it acts like a tiny, super strong magnet. It makes the water molecules in your tissues behave differently.
So it makes things light up.
Exactly. Tumors or blood clots glow brighter in the magnetic field of the MRI machine. It allows for early detection of disease. It's a life-saving application of F-block chemistry.
Incredible. Now, let's circle back to that hook from the start. The rare earth paradox.
Yes, the classic counterintuitive example. You might think rare earths are rare, but, as we said, chemically, they are quite abundant.
But there is a supply crisis? No. The news is always talking about how China controls the supply.
Yes, but we have to understand the reason for the crisis. It's not abundance, it's 2 other things. First, geography. Most of the easy-to-mine deposits are in just a few places. But the second, the science part, is separation.
The identical twins problem.
The identical twins problem. Because the lanthanoids are so similar, separating neodymium from praseodymium is incredibly difficult. You have to do hundreds of steps of extraction.
But we need them that badly.
We need them desperately. A single large wind turbine might need 5 to 10 kilograms of neodymium for its magnets.
Wow. 10 kilos just for the magnets in one turbine.
Yes. So we have a situation of abundance in the ground, but scarcity in the market. That is the crisis.
That clears it up perfectly. Okay, we've covered a lot. I want to make sure our listeners are ready for their exams. Let's do a cheat sheet rundown of the key exam safe lines.
Good idea. Let's break it down.
First up, catalysis. What's the line?
For catalysis, write this. Transition metals, like iron in the Haber process, are excellent catalysts because their partially filled orbitals allow for temporary bonding with reactants.
Got it. Temporary bonding. Next, alloys.
For alloys. Iron alloys like steel are structurally superior because adding elements like carbon or chromium adjust properties like hardness and corrosion resistance.
Simple enough. What about phosphors for screens?
For that, right, lanthanoid phosphors like europium and terbium are essential for converting light into specific, pure colors in screens and LEDs.
Okay, next up, magnets.
Neodymium iron boron and NiDe-Fe magnets are the strongest known permanent magnets, and they are essential for motors and turbines.
Analytical.
Gadolinium chelates act as MRI contrast agents, utilizing the paramagnetic properties of the gadolinium ion for diagnosis.
And finally, nuclear.
Uranium and plutonium are fissile materials used for nuclear energy, relying on the instability of the actinoid nucleus.
Those are golden, just connecting the element to the property and the application. So as we wrap up, what's the big picture?
The big picture is that D and F block elements are the specialist toolkit for modern technology. We started with that construction site analogy, and it really holds true.
You can't build a modern world with just bricks and mortar.
Exactly. You need the wiring, the magnets, the catalysts. Remember the smartphone.
The neodymium in the magnet, europium in the screen, copper in the wiring.
And the catalytic converter using those d orbitals to clean our air. We study these elements not to torture students, but because they enable modern civilization. from steel bridges to MRI machines.
That's the key takeaway. If you get that, you've mastered this unit.
Absolutely.
Well, next time you pick up your phone or see a wind turbine spinning, take a second to appreciate the incredible chemistry happening inside. It is all thanks to the DNF block. Thanks for listening.
Keep learning, everyone. Goodbye.